Hello, my name is Rinat Abdrashitov, and I'm presenting interactive exploration and refinement of facial expression using manifold learning. My collaborators are Fanny Chevalier and Karan Singh, and we're part of the GGP lab at the University of Toronto. If you have ever tried to animate faces, you surely know that it's a labor-intensive task requiring a sequential manipulation of many sliders. It's very common for a user to produce a set of slider values that generates unrealistic facial expressions, especially if the user is not closely familiar with facial anatomy or doesn't have extensive animation experience. If I were to give you two similar expressions and ask you to match them, it will still require you to adjust multiple values to make them look exactly the same. This makes the fine-tuning and exploration of similar expressions a difficult task. The main issue here is that the space of all facial expressions is extremely large. Let's think of it as an abstract blob for now. If our interface has 40 sliders, then we're dealing with a 40-dimensional space. If we randomly pick a face from this space, there's a very high chance that the result is an unrealistic face. That's because the subspace of natural expressions is much smaller than the whole space. And we want the user to have an option to only produce faces that belong to this subspace, which we call a face manifold. To do that, we learn a projection operator that, given any expression in the space, is able to find the closest natural expression that lies on the face manifold. The manifold and the projection operator are learned using the data collected from an animated movie. In fact, we learned two different manifolds for both the upper and lower parts of the face. We augment the traditional slider-based interface by automatically applying manifold projection operator whenever a user moves the slider. Here, the face on the left is the result of applying slider values directly, while the face on the right is the result of the projection. This allows to ensure that the user doesn't leave the subspace of natural expressions. The current projected values used to pose the face are shown as a red bar augmenting sliders background to quickly visualize the effect of the projection. We're able to prevent intersections between different parts of the rig, as well as cell geometry intersections. To stress test the system, we use a game controller to simultaneously change multiple and potentially conflicting parameters, and we can see that the result of the projection is constrained to the subspace of natural expressions. After posing the face, the user may find that the result is close to their preference, but may require fine-tuning to fit their artistic vision. We propose a novel interface to explore new neighbors of a particular face pose. We visualize the space of similar expressions around the current pose. The darker the green, the further from the manifold. When the user clicks on the current face pose, we show images of neighboring faces to help guide user to the desired pose. The animator can freely navigate within that neighboring space, allowing fine-tuning of facial expression while being aware of how close or far the result is from the manifold. To save the chosen pose, the user clicks on the bookmark button. If the user finds a plausible face but wants to see additional options, they can click the Re-Refine button to generate a new latent space for this face. Even though our manifold was trained on the animation data for a particular character, it does generalize well across different human characters. Now let's talk about evaluation. We first performed manifold quality assessment via crowdsourced study on Amazon mTurk. The main goal was to measure the presence of unnatural faces in the manifold and the quality of the projection operator. The main results of the study is that 89% of faces that were voted as unnatural by the users were voted natural after the projection onto the manifold. Next, we conducted a user study to find out how well our interface works in practice. The users were tasked with recreating given expressions using a traditional slider-based interface and our interface with manifold projection. The main results of this study were that on average, our interface, compared to the traditional slider interface, allowed users to complete the task faster, required less sliders to be activated, and the final result were closer to the goal. So what are the main limitations of our approach? Well, getting a strong sense of control is critical to creative authoring. Constraining the user to be on the space of a learned manifold does take away an element of full control over the output. As most data-driven methods, our approach is limited by the quality and richness of the data used to build the manifold. In the absence of a good representative dataset, of example face configurations, manifold projection will constrain the exploration to a small subspace of natural faces. But it also makes it possible to use a specific dataset as a way to intentionally bias the manifold to generate expressions that conform to a particular style. Thank you for watching.